Hello. In 2 hours, eh? Oh wow. Oh cool. I've never heard of that one. Uh, you prepared? Well, yeah, of course they would. Okay. Mm-hmm. Huh, that's interesting. Yeah, I've never looked at a contest that's not a math contest. I can't even really quite picture what would be on it because it seems like with the sciences, and this isn't a bash on the sciences. It's just by nature, but there is some stuff that you just have to know, right? Um, like you can't just figure out on your own that gravity is like 9.8 meters per second squared, right? Like you can like you have to be told that, and if you don't know that, then you're on your own. But the nice thing about math is that you could I could ask you a question on a topic that you've never considered, and you could probably figure it out. It would just take a long time, right? Yeah, yeah. Yeah, I'd love to see what they look like. Um, okay, well, pretty low turnout today. That's okay. I'll try to make this one go by pretty quick. This is one of the I think a little bit more challenging topics that we had, which was this is all the stuff that we did like with like the washer method and the disk method and finding the volume of those weird shapes, that kind of thing. So this is also the topic where Nick broke calculus, if you recall. So I think we fixed it though. I think we managed to piece everything back together. But in any case, yeah, I've gone ahead and I've written out the applications of integration unit, or like subunits, or whatever you want to call it, subsections. So I'll just kind of go over it sort of quickly. Like you guys do have this reference; it's on the website. If you want to know what the topics are, you can always message me, but it is available to you. It's on our website. So you can download a package that has a whole list of all of these things and things like that. So I'll go over it pretty quickly. First topic is average value of a function. I recall getting you guys to teach yourself that unit. I think that it was just a bad week. Like I had a bunch of PDs to go to, and I was away like 3 times that week or something. So I just was like, okay, you guys are going to teach yourself this. So I mean, the average value of a function, you just take the area. And then the integral between a and b, and then divide by b minus a. There's not a whole lot to it. So position, velocity, acceleration with integrals. So that's just being able to use an integral to go from acceleration to velocity to position, and effectively you'd have to solve for the constant in that case. Using accumulation functions. So accumulation functions are special types of integrals, the integrals that we've been using to capture the volume of different shapes, right? So kind of like looking at like a slice of a shape and saying, okay, that's the area, and then we're going to accumulate all that area to develop volume. So using those accumulation functions. And then the rest is pretty much all just methods of finding volume and area. So finding area between curves with respect to x. So kind of seeing how the area between two curves can sort of be a function of x. And then conversely, the same thing, just in the other direction. So that's units 4 and 5. The sixth one is finding the area between more than two curves. So that would be something like, finding the area between this shape and this shape and this shape, and you've got sort of three intersections. So how do you find the area between those shapes? Volumes with rectangular cross sections. So something like this, where we would have one of these sort of prism-like shapes, where if you took a cross section, you would get a rectangle. And then same with triangular or semicircle cross sections. So like maybe some kind of shape that looks like this, and if you take a cross section, you get like a little semicircle like that. Go ahead. This is chapter 8 in the textbook as well. Yeah, in the textbook we called it using the definite integral. And yeah, cool. Okay, and then section 9 is using the disk method. So that's basically cutting up your volume in terms of a disk. So that's usually when you're integrating along the x-axis like this, and you've got some kind of funny shape like that, and then all of the areas are a circle, right? So that would happen effective when you have a curve and you rotate that curve around the x-axis. We also covered using the disk method on a different axis. So like maybe you rotate your curve around the y-axis, and then you have to sort of change your variables and that fun stuff. And then the same with the washer method. So the washer method is kind of where you have the area between two curves, right? So maybe you've got another curve that you're rotating around the x-axis, and now you've got washers instead of disks, right? I think I remember at the time I kept getting those words mixed up. Every time I wanted to say washer, I said disk, and vice versa. But a disk has no hole in it. A washer does have a hole in it. And then same with that, finding the alternate axis. And then there's this one, arc length. And I was kind of surprised to see that, because it's not in our textbook. I mean, it is in the textbook, but it's part of the last chapter on parametric equations. So this textbook shows you how to calculate the arc length of a parametric curve. So basically a curve that's defined in two variables. And also it shows you how to find the arc length of a curve that's defined in polar coordinates, so where you're looking at the angle and the distance from the origin. But it does not show you how to calculate the arc length of a regular curve. So I decided what I would do is I wouldn't teach you like the understanding, and I'm not going to derive this formula. I'm just going to give it to you, and I want you all to just write it down and just have it on hand, because it's quite likely that this formula is just going to come up, and just to have it close by when you're working is going to be very useful. Typically, I encourage you to develop an understanding of a formula and understand where the formula comes from and how to derive it. But we just don't have time. Now is not the time to develop the understanding of the arc length formula. But if you do have a little bit of extra time, I challenge you to maybe look up a video or try to figure it out on your own. I mean, the gist of it, I'll just kind of quickly show you the gist of it. So, basically the way integrals work and these formulas work is that you sort of approximate it by splitting it up into small little bits, right? So basically, if we split this up and then made like straight lines, right, then that would be a pretty close approximation to the actual arc length. By the way, arc length just means like if this was a string and then you pulled it taut, how long would that string be? So you can imagine that if we did this, well, we would be using the distance formula, and the distance formula is basically an application of the Pythagorean theorem. So that would be like delta y squared plus delta x squared, like the change in the x plus the squared plus the change in the y squared. Take the square root of it. Just the Pythagorean theorem. With all these, and you'd add them all up, and then you can kind of imagine how integrals work, right? You take the limit as these little things get closer and closer together. So maybe you can get these like infinitesimally close to one another, right? Take a whole bunch of these little dots and then take the limit. And then the formula that you get, I've written it out here. So if you want to, this is the formula right here, by the way. So if you're asked to find the arc length between 2 points, A and B, of a curve, so that's basically saying, okay, so this length right here, let me make this nice and thick. So this length right here, if I were to if this was a string and I were to pull it taut, like nice and straight, how long would that be? And you can kind of see where the Pythagorean theorem sort of fits into it. Oops, that's too thick. But you end up taking the derivative of the function. You square that derivative, add 1 to it for some reason, take the square root of it, and then that's your function that you integrate. So so I'm glad that we're doing the FRQ today that I chose, because the FRQ, uses the arc length formula. So we'll get to see it in action today. So yeah, the question that I pulled out today. So by the way, let me know if you need me to scroll back up, because I do expect you to have this in your notes. So maybe take a second right now with your pencil just to quickly jot it down. It's also very easy to find on the internet, but it is not in your textbook. So yeah, we're going to use this formula today. So the FRQ that I chose was Unit 8 Part B. Unit 8 Part A I've assigned to you. That's due on Monday, I believe. But Part B I thought we would do together. And this is Part B. I've gone ahead and I just wrote it out ahead of time. I was getting kind of sick of taking screenshots and emailing them to myself and that sort of thing. So so here's the question. So we'll just take a second to sort of soak it all in. So we've got this function y equals 1 over x, right? But we're only really looking at in the first quadrant here. So we've got y equals 1 over x, and the region R is the area bounded between that function, y equals 1 over x, the line x equals 1, so this line right here, the line x equals k. We'll talk a little bit about what k is in a second, and the x-axis. So I've gone ahead and I've shaded it, and on the actual question, like the FRQ question, they provided a diagram as well. But if they didn't provide a diagram, I can't stress enough how important it is to make your own diagram, because as you are creating the diagram, it really becomes illuminated what you're doing. I can't imagine doing this question without a diagram. You kind of just need a diagram for these. And same with pictures as well. While I was solving the last question, I think it's part C, this question here, I didn't draw a diagram. I was like, yeah, I can do this. And then it didn't really make any sense to me. I was like, wait, what? The algebra doesn't work out here. I don't get it. This is too hard. And then I drew a picture, and then I realized I was rotating the region around the wrong axis. So so yeah, don't make the same mistake as me. Just draw a diagram to start off with, and your life will be much easier. Okay, so the first question is to find the area of R in terms of k. Oh, by the way, k is just a constant, which is greater than 1. So k you never have to worry about k like being over here or over here. K is always going to be to the right of 1. So let's talk a little bit about this. I thought maybe what we could do, we have 25 minutes left. So what I'd like to do is I'd like you to try this one yourself. I'm going to give you maybe 2 minutes for this one, and then I'll sort of interrupt you and see how far you got. Okay, so I'm going to give you 2 minutes, and I want you to try it. So get out your pencils and try this one out yourself. I'll leave the question up here so you can actually read it, and I think that should be enough info for you. So do part A. We'll worry about part B in a second. And you got 2 minutes. Go. Okay. Let's see how you did. So this one, it's not intended to be a super challenging question. It's kind of more of a warm-up. So let's see what we are asked to do. So we're asked to find the area of R. And the area of R is basically, it's just the area underneath the curve, right? The area underneath y equals 1 over x between 1 and k. So that's, like, we can just express that with an integral. So the endpoints of our integral are 1 and k, right? We're starting at 1, we're ending at k. It's okay that k is a variable. You know, k is just, I mean, it's a constant, but it's also a variable. So we're treating it as a constant, even though it is a variable. And then the function that we're integrating is 1 over x, and we're integrating with respect to x. So this is, I mean, the integral of 1 over x is just ln of x, right? So this is ln of x, and we're going from 1 to k. And I think you guys put brackets around it like this, right? Yeah, okay. I just want to make sure I'm consistent with you. I always forget the notation that you guys use. There's a lot of different ways of using this. The College Board, for example, does not use this notation. They use, oops, too big. They use this notation like that. So maybe I'll do this just so you can see that you can write it in a different way. And then this, of course, is ln of k minus ln of 1. Ln of 1 is 0. So this is ln of k. So wasn't too challenging of a question, I don't think. If you got stuck on it, maybe I would suggest practicing some integration. So going back to the textbook, I think chapter 7 would be a good chapter to sort of do some review. But yeah, that's that question. Not a whole lot to it. And I'll let you know about the way this one was marked. So they're looking for 3 things here. They wanted the definite integral, which is this, so writing that out. Finding the antiderivative, so finding that. And then getting the answer, which is that. So those are the 3 things that they're looking for. So this would be a check mark, check mark, check mark for full marks. So if you just went straight from here to here, you get 2 out of 3, even though you got the right answer. So I can't stress enough, show all of your work, show all of your steps. Don't skip any steps. It's just, there's no point, okay? Okay, now for part B, we're asked to write the expression, but do not evaluate in terms of k. So write the expression in terms of k. Don't evaluate the expression though. That gives the perimeter of R. So this is where we get to use our new formula that we just learned. So we're asked to find the perimeter. So the perimeter is made up of 4 curves in total. We have this curve here on the left. We have this curve here on the right. We have this curve at the bottom. And then we have this curve on the top. The first 3 are going to be super easy to calculate. They're just straight lines, so there's not a whole lot to it. That last curve on the top, that's where we need to use the arc length formula. So that's one of the reasons I chose this question, was that we got to actually use this arc length formula. So let's use the arc length formula. So let's split this up. I'm going to split it up into, I'll call this, I don't know, I'm just making stuff up here. I'll call this A, this side B, this side C, and this side D. Okay, just to make sure that we're not, you know, double counting anything or anything like that. So A is going to be, well, that's just our function evaluated at 1. So that's going to be just 1. So A has length 1 because this is the point like f of 1, and our function, I mean, let's call this f of x, right? F of x equals 1 over x, so that would be 1 over 1, which is equal to 1. So this distance right over here is 1. B is the distance from 1 to k, so this distance right here is k minus 1. So B is k minus 1. C is, well, our function evaluated at k, so that's going to be 1 over k. 1 over k. So those 3 are very straightforward to calculate. Like we've already done it. D, that's the hard one, the curve, the curvy bit. This is where we need to use our arc length function, okay? So the arc length function, again, just as a quick recap, so usually we refer to arc lengths using the letter S, not sure why. We go from the beginning to the end, A to B, of the square root of 1 plus dy by dx, all squared. Make no mistake, that is not the second order derivative. That is the derivative squared. Okay, so we multiply the derivative by itself, all with respect to x. So in this case, come on, x. In this case, well, we're going from in this case, we're going from 1 to k. Going from 1 to k. And let's figure out what dy by dx is. I'll just write that on the side. So dy by dx, that would be, well, our function is 1 over x. So that would be, I guess, negative 1 over x squared. Okay, so our function is looking something like this. I've got negative 1 over x squared, all squared, with respect to x. Oh, I guess my head is probably covering that, eh? So I'm going to have to move all of this stuff down. Oops. Give me 2 seconds here. There we go. Okay, so yeah, let's finish evaluating this. So this is the integral from 1 to k. Take the square root of 1. Now, if I square this, it becomes positive. I've got 1 over x to the power of 4 dx. Okay? And if we really wanted to, like, we could probably figure out how to integrate this, but we're not actually asked to evaluate this, right? We're just asked to write the expression, do not evaluate. So let's not waste our time trying to evaluate this. So our arc length, or sorry, I guess I should say perimeter, our perimeter, let's just finish writing this off. So d is equal to 1 to k square root 1 plus 1 over x to the 4 dx. Okay, so the perimeter is, let's call it p, and p is going to be equal to a plus b plus c plus d, which is equal to 1 plus k minus 1 plus 1 over k plus the integral from 1 to k of the square root of 1 plus 1 over x to the 4 dx. And we can clean this up a little bit, like this k cancels with, or sorry, that 1 cancels with that negative 1. And then, so long story short, all in, we're at k plus 1 over k plus the integral of 1 to k, the square root of 1 plus 1 over x to the 4 dx. And that's that. Let's see how this one is marked. I've got the thing up here. Okay, so the way they've marked this one, there's 3 things they're looking for. They want f prime of x, they want the integrand, and they want the expression. So let's see what mark I would have got. So dy by dx, aha, I figured that out. So that's f prime of x, so I get 1 check mark. The integrand, did I get the integrand right? Yes, I did. And the expression, yes, I did. So they're looking for little key spots in the solution. Okay, and I think we got all 3 there. Okay, so this is kind of the next part. Is we spent a lot of time doing these types of problems. So I'm hoping that there's a little bit of recollection here. Thing is, it was a while ago, so you may have forgotten. So the idea is that the region R is rotated about the x-axis. Okay, so we've got our, let me just draw it out again so I don't have to keep scrolling up and down. So here's our Cartesian plane, and I've got this function here. It looks something like this. And here's k, and we're going from 1. And this is the region R. And here's the x-axis, and here's the y-axis. Okay. Now we're rotating it around the x-axis. Okay, so now all of a sudden we've got this 3D shape like this. We're rotating it around the x-axis, and we get this kind of horn-looking shape, right? So it kind of tapers off as it gets further and further away from the origin. Furthermore, they're saying that as k increases without bound, so now k is just going to keep on going without bound. So basically, we're looking at the limit as k goes to infinity of this shape. They want us to find the volume of the solid or show that the volume is infinite. So we have to do one of those two things. I have a feeling, I think a student, when we first were learning this stuff, actually requested that we do this problem. It was the horn of, the horn of Gabriel, which, as far as I understand, is exactly this shape. So here we are, better late than never. Maybe we actually did do it. I don't actually remember if we ended up covering the horn of Gabriel, but here it is, in any case. So it's like a super long horn that is infinite in length, but well, hopefully we'll find that it's finite in volume. So I'm gonna give you, let's say, I'm gonna give you 5 full minutes for this one, and we'll see how far you get in the 5 minutes, and then we'll solve it, and we'll call it a day. So I'll start the timer in just a second. 5 minutes. And oh, by the way, I made a little hint here. The hint is you may want to use this formula here. I'll bring it over. Oops. Come on. I'll bring it over here so you have access to that. Okay. Okay, so 5 minutes starting now. Oops, that's 2 minutes. 5 minutes. Okay. So get your pencils out and give this one a shot. See if you remember how to do this. Okay, time's up, guys. How was that? Was that too much time or too little time? Or was it just right? Just right? Okay, cool. So, we're gonna find this area. So the idea here is that we're gonna be like integrating with respect to the area, right? So every time, like if I were to take a cross section of this function, I need to figure out what the area of this circle is, right? So in order to find the area of a circle, you need to find the radius, right? But let's make that radius go right from the origin of, or not the origin, but the x-axis right up to the function. The radius here is what? It's f of x, right? So in this case, the radius is 1 over x. So the area of the circle, a of x, is equal to, well, pi r squared. So pi times 1 over x squared. So the volume of this is going to be, well, v is going from 1 to k. Now we'll deal with the limit in a second. But we're going from 1 to k of, well, pi r squared. So pi times 1 over x. Oops, not to the power of x. Eraser. Dx. Okay? And, well, we can factor out that pi. So this is pi times the integral from 1 to k of 1 over x squared dx. And, well, what's this equal to? Well, so I'm going to turn this into x to the negative 2, because that's how I like to think. So what happens? The exponent gets bigger, so we would get x to the negative 1, and then we divide by that, so minus x to the negative 1, and we're multiplying this by pi, and we're going from 1 to k. Okay, so so this is equal to, I should have a bunch of equal signs. Well, I've got pi times, and let's introduce some brackets here, negative k to the negative 1, or let's go back to a fraction, so negative 1 over k minus negative 1 over 1, so plus 1, okay? And remember that we're actually taking the limit as this goes to infinity, right? K is increasing without bound. So the limit as k goes to infinity of this function, pi times negative 1 over k plus 1. Well, 1 over k just goes to 0. So this is the limit, or I've already evaluated the limit. It's just equal to pi times 1, or in other words, it's just equal to pi. So this is the final area. So worked out pretty well. Let's see what the College Board, how they would mark this one. So they're looking again for 3 things here. They want the improper integral expression. So the improper integral expression. So, ooh, you know what? Actually, I would have missed that. Yeah, because they're looking for the improper integral expression. I decided that I would leave that for the end, but they didn't want that. So I guess I would have got 2 marks out of 3, assuming I got everything else right. So what they really wanted is us to look at, to include the limit right at the very beginning. So so I guess I suppose that I taught this in a way that is not beneficial to you. So next time, when it comes to an improper integral, like if you have to take a limit, throw the expression in right at the very beginning, because that's what they want. So this is what they want. So they want the improper integral expression. They want a definite integral with limit notation. So I guess that's what that is as well. So I guess actually what they wanted 2 things, because technically this isn't an improper integral expression. So I actually even failed twice. I would have got just 1 mark out of 3. They want this as well. They want that our volume is the limit from, or not even the limit, it's just the integral from 1 to infinity of pi times 1 over x squared dx. So this is actually their first mark. This is their second mark, and then the final answer is their third mark. So imagine that. Like, I did all that calculus, and I feel like I demonstrated understanding there. And if I was marking your work and you did the same thing as me, I would say that you demonstrated understanding. Excuse me. That's not how they mark this one. So, excuse me, just inhaled my spit. So I guess the lesson here is that we should be looking for the expressions that they want us to write down. So in a lot of ways, I don't really like this method of teaching, just like trying to look for ways of getting grades, but I think it's probably relevant to you. I think that, yeah, what's that? Pi r squared. Yeah, area of a circle is pi r squared. So r squared is this thing, there's the pi. Yeah. So yeah, I guess what the lesson here is, maybe it is a good thing that I messed up. I did all the algebra right, did all the calculus without any mistakes, but I didn't write the expressions that they're looking for. So I would have got just 1 out of 3 there, which come to think of it, it's kind of shocking. So yeah, think about the expressions that they're looking for. They're going to want to see a definite integral, an improper integral. They're going to want to see a proper integral with a limit in the front of it. So try to just write as many things that you think that they would want to see, and then they have to give you the marks. So okay, exit slip today. I don't want to make it too hard. Let's say, I know. Exit slip for today. So using Desmos for typesetting. So using Desmos for typesetting, because I don't think you can type this out on your own in plain text. Write the arc length formula. Okay, so I'm not going to scroll up. You gotta search for it yourself. Make it look nice in Desmos in the way that Desmos works, and then copy and paste the plain text into the exit slip. So that's your exit slip for today. So yeah, I guess tomorrow. Wow, tomorrow's our last calculus class. That's crazy. Yeah, so tomorrow I guess we're gonna do unit 10. So we're gonna skip unit 9. I'm just gonna do unit 10. So and that's I believe on sequences and series. So wow, holy smokes! I'm not sure if I'm ready. I've grown kind of attached to this. So yeah. Anyway, I'll see you guys tomorrow. And if you have any questions about anything, don't hesitate to reach out. And yeah, take care. Bye bye. Oh yeah, what's up? Yes. Yeah. 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 Big change from grade 7. Yeah, absolutely. Yeah, no, I'll be doing this again next year, as far as I know. I mean, things can always change, right? But the plan is that I'll do this again next year. Yeah, I think next year I'll have a little more preparation under my belt. Typically, like when you teach a new class, you usually spend the summer preparing for it, right? And coming up with worksheets and lesson plans and things like that. And just due to the situation, like it's not like it was anyone's fault, but it's just due to the unusual situation that we found ourselves in. I had 4 days to prepare for it. So I've kind of been making it up as we go along. And I'm sure you're able to tell that some days I'm like running around like a chicken with his head cut off. But yeah, I think next year I'll have a little more of a outlook and kind of long-term plan and that sort of thing. So I'm really looking forward to next year. But this has been great. I mean, you guys have been extremely understanding and very respectful anytime I make a mistake. So yeah, thank you very much for being a part of it. I've learned a lot from all of you, and not just about calculus, but just about teaching in general and that kind of thing. So, but yeah, we still have tomorrow. So yeah, that'll be fun. And then also we still have like the advanced math project that we're gonna do. So we'll start talking about that after all of your AP stuff is over. What was the date that we said? I think it was like the 17th. Or no, that's a Sunday. The 19th? 21st, yeah. Okay. So we've got a class tomorrow, and then you've got I think, what is it? Comp Sci on Monday? Did I make that up? Physics is on Monday. Okay, and then Calc is on Tuesday, the 12th. And then you got a bunch of other exams after that. And then we'll pick up where we left off on the 21st. Okay. How about this? How about why don't you just have the rest of the week off? I can imagine you guys are going to be exhausted. So why don't we take the rest of the week off then, and we'll resume our live streams on the 25th. Okay? So we'll start again on the 25th. So we'll take a 2-week break. Well, it's not really a break for you guys. But we'll take a pause from the videos, and we'll meet back on the 25th. So yeah, sound good? Okay, great. I'll talk to you guys tomorrow then. Okay, bye bye. And goodbye, YouTube. Take care.